Okay, welcome to lecture 14. What we're going to cover today is online games. So the idea of this lecture is to introduce some of the different types of game that can be played online, as well as some of the architectural and technological choices that are made when you're building an online game. So there's a little bit of a internet scale application sort of motivation here in terms of explaining, because online games, especially the massive multiplayer online games, are certainly internet scale applications. And there's the sort of secondary or other motivation behind this talk is to get you thinking about your second mini project. So I'm going to talk about various different kinds of online game, and maybe you'll decide, oh, this one looks really fun and interesting, maybe I'll do this kind of online game. So we're going to start with a little introduction, run through some architecture and technological choices, talk a little bit about game engines, middleware, a couple of concrete examples. So EVE Online is a sort of interesting example of a massive multiplayer online game, as well as and Second Life is sort of a game, but a very sort of free and easy kind of game. And then some of the sort of augmented reality games, just another sort of paradigm that's emerging, and some of the applications of games in science, so that's something that kind of interests me, and some of the issues that are encountered. So in this section, I'm just going to say a little bit about the different types of online game. This is sort of very sort of simplistic overview to get you thinking a little bit about the implementation of your second mini projects. So sort of games you can have are a couple of players turn taking, several players taking turns, and small groups like interacting in real time, and then large groups interacting in real time. So two-player turn taking, we've got board games, simple board games like tic-tac-toe, chess, backgammon, these kind of things. And then we've got strategy games, battleships, that kind of stuff. So all familiar with chess. So one player makes a move, and they hit the clock and pass the move to the other player, and the other player makes the move, and so on. Then you've got small groups, but you're still taking turns with the small groups. So like strategy games, such as Civilization, or things like Monopoly, Trivial Pursuits, Risk, and so on, these kind of traditional board game type things. So in Civilization, I think never played it, but each person controls some territory, some armies or whatever, and they have to build up their civilization and conquer other civilizations and all this kind of stuff. But I think it's a turn-based game in which people take turns to make their changes to the world and attack people and so on. And then so third type of game are small groups that are interacting in real time. So we've got card games such as poker, racing, fighting, first-person shooters, sometimes known as a multiplayer online game. And typically you have a series of self-contained independent multiplayer matches. It's not like some epic world is unfolding over hundreds of years. It's just like short race, a short fight, maybe 5 minutes, maybe 10 minutes, and then job done, all finished, everyone goes home, has a cup of tea. So, poker, again, I've never played this, but online, you have your avatar, and you're kind of interacting in real time. So the interactions aren't just the play of the cards, which would be a turn-taking game. So there is a turn-taking component to it, but there's also a sort of judging about, who's bluffing who and all this kind of stuff. So there's a little bit of real-time interaction going on as well. Car racing, classic example, right? You got like 4 or 5 cars. They're all having a single race. Each person controls the car, and then whoever wins kind of thing. Unreal Tournament, so you're sort of creeping around dungeons or whatever, maybe with several other players in the dungeon as well, maybe some monsters, and you try to kill each other and kill the monsters and so on. And Street Fighter, like one-to-one, sort of kicking each other and hitting each other and so on. And Grand Theft Auto Online, it's sort of in the boundary between a massive multiplayer online game and a sort of small group real-time interaction game, because you're sort of, not necessarily, I don't know about the latest version, but you sort of typically got small sort of missions and so on, which are fairly small and fairly self-contained. You're not interacting within a single vast world shared by tens of thousands of users. So I'm putting it in this category. So it might be a bit of blurring with the other categories. Might be a bit of blurring with this, in fact. So we've got large groups, real-time interactions, and this is called a massive multiplayer online game, MMO game. You've got a large number of people playing simultaneously within an online world. So EVE Online I'm going to talk about in more detail later, but World of Warcraft is a sort of good example of this. And Second Life is almost a game, so I'm going to include it as well. So here we have a a vast environment with tens of thousands, possibly hundreds of thousands of players interacting in that environment. So this is a true sort of internet scale application type game. So yeah, you've got EVE Online, which I said I'm going to talk about a little bit later, but you teams collaborate in building worlds and carrying out different kinds of missions and so on. World of Warcraft, I think it's a bit more mission-based, but you can have quite a large number of players interacting within each environment. It's sort of very popular one, sort of wizards and warlocks, all this kind of stuff. And Second Life. So again, I'm going to talk about it in more detail later, but it's a sort of complete. It's what it says on the tin. Really, the idea is it's a second virtual world in which you have a second life, in which you can be anything, do anything. But you can also do constructive things or destructive things. It's a game, but it's a very open-ended game in which most of the content's user-generated. So most video games are a form of virtual reality. This is a classic virtual reality game, right? But there's starting to be more games using augmented reality where the game is overlaid on top of the real environment, embedded in the everyday world to some extent. I'm going to talk about these later. Okay, architecture. So we're trying to run games. Now, some games are run very simply on very light computer resources, and other games are going to require very heavy computer resources. So some games run easily on a single central server. Other games you're going to have to deploy across large numbers of servers. And I'm going to talk about the sort of single versus single-sharded and multi-sharded architectures, and say a little bit about, well, say almost nothing in fact, but you can actually run games on a peer-to-peer basis where all the peers are communicating amongst each other and there's no single central server, but it's a point to register, but it's not a point I'm going to cover in any detail. So, if you're going to have an online game, you need some that's not peer-to-peer, you're going to need some kind of game server. It's sometimes called a host or a shard, and you're receiving messages to and from this central server in order to play the game. So, with turn-taking games, this is dead easy, right? Player 1 changes the state of the game. Player 2 is just sitting there, waiting away, looking at the stars. And then when the state of the game changes, the server notifies player 1. Player 2 notifies the server about their move, and the server notifies the first player about the move that was made by the second player. So this is like classic chess kind of game. Very easy to distribute games between servers. Very weak time constraints because most of the time people are just sitting around waiting for the other player. So all you have to do is send messages to the server, wait for the game to be changed by the other player. So no problems really with turn-taking games, with building online games. Online games have much more problems. There's much more hard technology or challenging technology behind real-time games, even with multiplayer, even with small numbers of players, the real-time constraints can be quite severe. So in this case, both players are sending their actions to the central server. The server's calculating how these actions affect the environment and sending new object positions back to the player. And then on the player's computers, you're rendering the objects. So this is really tough time constraints. We're running at 25 frames per second. You have to do this every 40 milliseconds. So, never mind how long it takes, you've got to send these messages, update the state of the world, and then send those messages back within 40 milliseconds. And you're possibly doing that for large numbers of players if you're trying to get real-time interactions with large numbers of players. So it's challenging. So on the client side, what the player has to do is sample the clock, find the start time, sample the user inputs, what they've actually done to the world, package all this up, send the movement commands, and send the movement command off to the server. And then once it's sent what it does to the world, so maybe it's like move the steering wheel, something like that, that's what's being sent up to the server. And then it updates, then it receives the packets from the server from the network and uses these to determine the visible objects in their state. So let's suppose the player sort of moves the steering wheel like that, sends that off to the server, and then receives back from the server the new car position, and then on the client side, it'll render the new car position, new position of the road, and what it can see, and so on and so forth, and calculate any interactions between this player's car and another player's car, for example. And then it does a sample clock to find the end time, and then the simulation time for the next frame. That's so it can calculate, the next positions and possibly do a bit of physics and so on. And on the server side, it finds start time, reads client input messages from the network, executes the actions on the simulated world running on the server, and then sends the new positions of the objects and their states back to the client. And so package up visual objects and world states, send back to the clients, and then it works out how long all that took, so that because it's real time, and there'll be a bit of fudging. It sort of has to keep track of simulation time and tell the clients which bit of time to render and how long it is and so forth. And with these real-time interactions, there's obviously a limit to the number of players that can run on each server. So there's a figure of maybe 5,000 active players per server. Only 5,000 people can interact in real time on a single server, and even that seems quite a lot to me, because each server has a limited amount of bandwidth, CPU and RAM. So doing all this back and forth with a 40 millisecond loop, even doing it at 5,000 players is an enormous challenge. So there's a limited number of players that can play the game on a single server. So how can you handle that at an architectural level? Well, one way you can do this is just limit the number of players on each server. So each server runs a particular game, and there's a limit of the number of people that can play that game on that server. So players on the same server play the same game, same environment, but players in different servers cannot interact. So supposing you had this game that had this, let's say a forest. Let's say it's a forest game, and there's a big forest in this simulated environment. Now, on one server, all the players that are playing on one server can walk around the forest and see each other, but they can't see any of the players that are playing on a different server because those two environments are completely decoupled from each other. So they can only interact with the other players that are on that server. And that's this distinction between single-sharded and multi-sharded. So a single-sharded game is there's a single instance of the game environment, so any player can move to any other location in the game, and any player can interact with any other player. So there's no limitations on player-to-player interactions or which bit of the environment a player can enter. And multi-sharded, you've got a fixed number of people playing the game on each server. And they can only interact with other players on the same server. And then maybe you'll choose to hang out on a particular server with particular friends, right? You want to play the game with a group of people. Maybe it's a wedding. You decide, well, this is boring, all this religious stuff. Let's go and play a game. So you can just all go and hang out on the same server in the same environment. So that's a single-sharded, single server or group of servers, and all the players are interacting with each other on the same environment. And you've got multi-sharded, you split the players, and you can split the players in a couple of ways, which I'll explain. Yeah, that's dividing the players. Sorry. So that's how. So the players have a single copy of the entire game on each server, and the players can all interact with each other in the entire game. The other way you can do this is divide the environment. So you can run bits of the environment on different servers, and then hand over the players as they move between parts of the environment. So each room or several rooms are on a single server, and if player moves between servers, the servers pass appropriate information to each other. So this is the idea here. So this is our environment. So on a sort of classic multi-sharded architecture, an entire copy of this would run on each server, but a limited number of players could interact within this entire copy. But in this way, if we divide the environment, then we can do it in a different way, which is a bit more natural. So we can run like rooms 1, 2, and 3 on server 1, and rooms 4, 5, and 6 on server 2. And so all the players here, and when this player here sort of moves across to this room, then we just copy their details across to that server and do a sort of handover process. That's how to divide the environment, and Second Life does this kind of stuff, as does EVE Online. This creates its own set of problems, right? We can have popular areas. So to complete a particular quest on World of Warcraft, for example, maybe you've got to go to this dungeon to dig up some treasure, let's suppose, or find a magic spell or something like that. So everyone who wants to complete that quest has to go to this particular part of the environment, and so this can completely overload the server. If everyone needs to go to room 3, let's suppose, then all the players are going to go there, and it's going to completely overload this server. So to handle this, you've either got to restrict the number of people that can enter a particular room, but then that's going to be really irritating. If to finish the quest, the most popular quest, let's say, you have to enter the room and then you've got to queue up outside. I mean, it's realistic, that's the real world, but this is a game, we want to have fun here. So this can be a real problem. It can annoy players, particularly if they're part of a popular quest. If you've got a massive environment and a huge number of quests, then the problem of player density becomes less of an issue. But the problem is content's expensive. If you've got to provide millions of quests to keep everyone happy and ensure that they're evenly distributed across the environment, that's going to cost you a lot of money. And if you want to automatically generate content, then that's a problem because it's typically low quality. You can't automatically generate quests or exciting things. You've got to have someone actually do it themselves. So I'll explain how Second Life and EVE Online handle this problem, but World of Warcraft, I think, is multi-sharded, and you just basically, you've got a limited number of players that can interact with each other. And so even with the so the other way to do it is you can engineer the game, and I'll explain how EVE Online does this, to encourage users to move to less popular parts. So if you find that you've got a clustering of players in one particular part, you just change the parameters of the game a little bit, and then to encourage them to disperse a little bit, and so you can run them on multiple servers. So 40 milliseconds, not a lot of time to communicate between players and servers, so you can lead to a bit laggy, and no one wants to play laggy games. You sort of turn the wheel, and like 5 minutes later your car moves, and it's almost impossible to control. It's like same sort of problem they have when they try and drive like rovers on Mars and stuff. You know, any control signals take so long to reach the rover and the visual feedback to come back. It's very difficult to control. So it's not a lot of time, and it's not fun to play laggy games. So how can you handle this problem? Well, one way you can do this is to predict. If you carry it, you have like a local copy of the game, and you have a server copy of the game, and you for many of the client's actions, you can just update them locally because you're just hitting a rock. That rock, you know, exists in all of the copies of the game environment, and you know that what happens when you hit that rock. It doesn't affect any of the other players. So you calculate the client's movement locally, update the state of the world on the player's computer, and you just assume that the server will acknowledge this. You still need to send the information to the server so that the other player can see you hit that rock. But since that rock doesn't affect anyone else, you can basically calculate, you can display to the server, to the player, you know, the crunching of their bonnet on the rock without worrying that the server will reject it or whatever. And then you might need to do a little bit of correction at the server side, particularly when you're in a racing game. You're dealing with two cars racing against each other, maybe interacting with each other. It gets a bit more complex. So as I said, you might do this by having the same game engine running on the client and server. You could run everything on the client side and just report what happens. So, for example, I like bashing someone on the head with my sword, and then on the client side, it just reports to the client that I killed that player. But this could lead to cheating. But you might want to, if you're running like military simulations or a peer-to-peer game, then that's fine because you're not worried about cheating. You're just worried about getting the most, snappy response time. You can also improve the response time by changing the server location. So typically large MMO games hosted on game company servers, but there's a finite, light travels electromagnetic waves travel pretty fast, but there's still a certain amount of time, and you've got like routers doing all this kind of stuff. So there will be a bit of a lag with that. The other way to do this is have what's called a listen server. So that runs on one of the player's computers and enables a small number of players to play on a local area network, and you get much faster response time in that sense. But then because you're running one of the server on one of the player's computers, that can create limitations for that player in terms of CPU, RAM, bandwidth, and so on. So that's the idea. So these are all the other players running on different computers, and then one of the players the server's running on one of the player's computers, or you could even put it on a separate one. So this works fine over a local area network. If you're playing a game with a few mates, you can get much faster response times with a listen server. Peer-to-peer architecture, well, you've got no single authoritative node. So I can't remember if this comes after the peer-to-peer network lecture, I think. So you've got a sort of this kind of interaction. So all the players are sort of broadcasting their changes to the state of the world to the other players, and you can have various methods for checking that they're actually accurate. Can be difficult to synchronize, but could be used with strategy games. So for example, if you're taking turns, then you could just broadcast your next move, or if there's fairly slow movements of the game, or certain kinds of games will be able to map quite nicely onto this kind of architecture, other ones less so. Okay, so that's just a little bit about some of the architectural compromises, constraints with different kinds of games. I'm going to say a little bit about technology now. A little bit about HTTP for games, and a little bit about TCP UDP. Now you can implement games using HTTP, web services, and so on, but then you get all this problem with one-way interaction. So if you're doing GET, POST, etc., that's fine. This client initiates communication, the server sends back the response. But this has a problem because if you've got two players, then you either got to do that for every interaction, and the clients have constantly got to be polling the server, because you've only got one-way interaction. As I said, you can use WebSockets or HTTP long polling to get around these problems. And I think IBM has this kind of game framework called PowerUp, which uses HTTP. So you could use HTTP, and it'd be quite a nice, neat solution for that. But sockets are much better for games, I think, because you've got two-way communication between client and server without any fiddly, hacky stuff, and you can get high reliability and low latency. So in your second mini project, my recommendation is sockets, although if you want to, you can use WebSockets. And with implementations of online games, you typically have this debate about whether to use TCP or UDP. I'm going to cover these in more detail in the next term, but just to sort of summarize, with TCP you can have straightforward, persistent connections, reliable messaging, and arbitrary sized packets. So TCP is like wonderful. It's nice and reliable. You can have streams, do all this kind of stuff. But you have this issue called TCP packet throttling. So on 3G and Wi-Fi, when packets are lost, you want a packet to be sent absolutely immediately because of the real-time constraints of the game. But TCP has this thing called congestion control. So when the network's really congested, to sort of try and reduce that connection, it sort of waits maybe up to 1,000 milliseconds before resending a packet. So with TCP, you can have like delay up to a second, which is obviously completely rubbish if you're trying to do a racing game or something like that. Whereas UDP is completely, fire and forget. There's no mechanisms for persistent connections, reliability, and so on. But it can work a lot faster because it doesn't have all these higher level mechanisms to ensure reliability. So if you implement your own reliability, you can get much faster, much tighter response times by implementing your game over UDP in a game-specific way. So there might be specific requirements for reliability or persistent connections, and you can put them on top of UDP without the packet throttling, and that's what a lot of games do. So the debate over TCP and UDP depends on really on what you need to do. So with World of Warcraft, for example, does run on TCP, and it has latency because of the way in which the game is written. So there aren't player-to-player collisions within World of Warcraft. There's only environment player collisions, which is easy to calculate locally. And attacks aren't some kind of elaborate sort of calculation of swords hitting swords or something. You just sort of attack an entity, and maybe it's probably a bit like Dungeons & Dragons. I've never played it, but you just sort of start the attack, and maybe it's some kind of dice throw or something. So with World of Warcraft, you can run it over TCP without the latency becoming apparent because of the nature of the game and the way the game's written. If you had like real-time interactions like a racing game, then it'd be very hard to run over TCP because under some conditions, it would just fall over and have horrible latency problems and laggy gameplay. So choice of TCP over UDP depends on whether latency matters and whether you can hide it if it does matter. So HTTP, you might use for some parts of the game. You're probably going to use TCP sockets if you're sending packets and occasional delay is okay. And if it's a real-time game with tight constraints, you're probably going to use UDP and handle your own reliability mechanisms. And the reliability thing might be less important. If the network's really congested and it loses one packet, well, maybe the next one's got the next state of the game, and that's the one you want anyway, perhaps. Okay, so game engines middleware. So that's all this is all the sort of previous section was all about the low-level tech like TCP, UDP, various architectural choices, all this kind of stuff. But a lot of people don't bother with any of that stuff because developing massive multiplayer online games, it's laborious, labor-intensive, highly specialized. So I'm not an expert in this. It's just an overview. To really drill down into it, people spend 3 years, doing a game programming course or whatever. To save all that hassle, to just produce the games, that you can use what's called a game engine and MMO middleware to do some of the work. So people have built these frameworks that enable you to develop games much more easily than if you tried to do all the programming and the graphics and the networking all from scratch. So game engines let people build and run video games, so they do all the rendering, they do the physics, collision detection, so on, sounds, and the scripting. Some of them have networking capabilities as well, and they can even be combined with MMO middleware as well. So you can take these solutions off the shelf and then just adapt them, and you're going to save yourself a huge amount of work. So Big World, for example, is a middleware for game development. It has the game engine, content creation tools, automatic fault tolerance, server balancing. So, powers World of Tanks with 90 million players. So, this kind of technology is what you'd be using if you were trying to build a game practically, it's much cheaper to pay for this middleware than to pay for developers to do a bad job of developing it, from scratch. Okay, so now I'm going to cover a couple of games just to give you an example of how the technological architectural compromises, and also because these are both examples of large-scale internet applications. So EVE Online is a massive multiplayer online role-playing game. Apparently there were 500,000, 500,000 subscribers in 2013, and it's like a science fiction space setting, 5,000 star systems, and it's all player-driven. So the fun of the game is the interactions with other players, not some kind of quest thing that's generated by content creation people. And it's got its own currency, which can't be converted to real currency. So there's a little bit of probably a slightly fake screenshot. And so how this game works is people do in-game professions, maybe do mining, piracy, manufacturing, trading, exploration, or combat. And they work together in corporations to carry out these different tasks. It's a single shard architecture, so any player can go to any other point in the game. Any player can interact with any other player, and there's like an economy within the game. And so if you do lots of mining and discover a new resource, then that will affect the entire economy of the game. So again, that's what makes it fun. So you've got 500,000 people interacting with this online environment, and you can interact with any parts. It makes it feel more realistic than just 5,000 people on a single server. That's the sort of the architecture of the thing. So fairly big, lots of servers. But the servers are coordinated with each other, so you have this single shard architecture. So what they do is they're dividing the environment across all these different servers. And they can manage this single shard architecture for a couple of reasons. So firstly, it's space, right? So planets, empty space, and all the rest of it, it's dead easy to generate automatically, algorithmically, using computers. So you can just generate different planetary systems, stars, space dust, all this kind of stuff. It's very easy to generate just by writing a bit of code. So you've got procedurally generated physical landscape. And then you've got combined with user-generated content. So it's the users who are building the spaceships, who are like doing the mining, maybe building cities, spaceports, and so on. So the content's generated by the players themselves. So that enables you to have a lot of content superimposed on this procedurally generated physical landscape. And then the people who run this game are then manipulating the environment and the game rules to balance the server load so that they attract people to different parts of the landscape, so that you don't get too much server load overload of the server that's running that particular star system or landscape. So users are building ships, mining materials, and so on, and they're interacting in different ways, so fleets, battles, chats, and so on, and different kinds of social interactions, chat, team cooperation, economic activity. So I had a friend who played this a bit, and he found some team and lots of chat and coordination to make sure they all played were present for the important battles and so on and so forth. So they hit this problem with a single shard architecture, that the ULI solar system was better connected than the others. So this attracted all the merchants who went there to sell stuff, and then all the buyers went there to buy stuff. And then there was one server running the star system. So one way they could have done it is packaged up the ULI in a more fine-grained way, but maybe that wasn't easy for their architecture, I'm not sure. So what they did to try and address this problem was that they manipulated the game environment. They added some special new jumps around the star system to lessen its appeal. So it ceased to become the central hub for buying and selling stuff, because there were other better connected hubs. And so in fact, it turned out there was a new best location called JITA, and so all the players ended up moving to JITA instead. So they just said, never mind, we just run it on a dedicated high-spec machine. So they did a bit of a hack, but you can imagine if JITA became even more popular, they'd have to think of another way and make JITA less popular by adding some more jumps, or changing the way in which people sold or bought stuff, or whatever. So they basically hacked the game so that the servers could handle the load. That's how it worked. So a little bit about Second Life as well. So Second Life, was this massive thing, in the first 10 years of this millennium, I suppose. It was like this whole dream of a second virtual environment that sort of in which you could do anything, be anything. Companies moved into Second Life and so on and so forth. But now it's sort of died away, and I think it's a bit desolate, largely empty, and dedicated to other things. So it's kind of a game, a bit like EVE Online, but with even less constraints on what people do in that environment. You could see it as a game with entirely user-generated content. So you had 126 million users in 2009, now largely forgotten. So all the content, so it's an interesting example, which is why I'm giving it to you here. So here we have all the content user generated. So users create virtual representations of themselves. They build buildings, shops, and they interact with each other within these buildings and shops and islands or whatever, so they can socialize, build new content, trade virtual property and services. People got married, people have relationships, all this kind of stuff. There's a virtual currency, the Linden dollar, which is exchangeable with real-world currency. So this is the exchange rate going up to 2011. So it's like 253 Linden dollars per US dollar. So this is a picture, sort of thing it looks like. People create their avatars, they can move around the environment, and each piece of the environment is managed on different servers, and somehow they've jigged things so that different parts, so that now, as far as I'm aware, you don't have this issue of massive clustering of players within single environments, single parts of the environment. So yeah, each server core handles an area Second Life. Assets are given these unique IDs, and they've got physics simulations, usual game engine stuff. And then you pass the gate users between servers as they move in the environment. And a lot of interesting applications as well, which is why I liked it. It's got like social, education, arts. People did various artworks of art. People have business meetings there, religious meetings. There were even virtual embassies. People have relationships. And it's been used a bit for AI research as well. So how it worked is that the people managing it, Linden Labs I think it was, they had areas of land within Second Life. And then people could buy areas of land and build stuff on them. So companies got interested for a while, and they had like meeting places, and you could like go and try on like the latest Reebok trainers or whatever within the Reebok store, or Coke, built their own little thing. So all the companies spent some money there building their corporate presence in Second Life, believing it was the next big thing. So interesting example of a completely open-ended game. So another type of game I would just want to sort of talk about towards the end here is augmented reality games, partly because you might find it, compelling for your second mini project. So we've got all this processing speed and hardware all the time. Most people have got smartphones, so now it's relatively easy to build a game that's overlaid on the real environment. So we've got Google Cardboard, which lets you, you sort of look through the Google Cardboard, and this is your phone here, and so you can have like use augmented reality with Google Cardboard, or you can do it just more straightforwardly just by holding your phone and like scanning the environment. So most of you have probably heard of Pokemon Go, the sort of next big thing in games, in smartphone games. So you've got 20 million active users. So you can capture, I think you can go around the world and with your phone you can see with augmented reality particular Pokemon Go creatures, and you can capture, battle and train these virtual creatures. So this is sort of a couple of screenshots. So you point your phone at this particular point in the grass and you can see this turtle thing. And as you move your phone, but you see a different bit of the environment, so maybe you see this sort of weird chicken thing. And then we got Ingress, another MMO augmented reality game developed by Google. So the Earth have these portals, and you can view them with your scanner or your mobile phone. You can capture, modify the portals, and they had a bit of corporate presence here. The companies could pay for their locations to be used as portals. So this guy is, looking at this portal, and this is like a display of what he'd see, through his phone. And then this is a little bit of a board game where you've got players controlling these monsters on this sort of live game board. So using your phone, you can see these monsters interacting in this board, and you can play with other players and so on. So that's just a little bit of an overview of the different types of game, different types of architectural choices, different types of technologies to use to implement these games. Just going to finish with a little look on what's called serious games. So games are a great way of testing and developing ideas about AI because you've got a sort of a simplified environment that you can control with computers and interact with programmatically. So it's a great way of testing different ideas. So there's like a lot of work on military training within game environments, war planning, and also artificial intelligence research. So it's a lot cheaper to train your soldiers on simulators than have them running around in the environment or actually fighting each other kind of thing. And then flight simulators is a classic example. And you've got these battlefield simulators as well. So you've got this, if you want to learn how to sort of shoot people from this vehicle, you can do all that in a virtual environment, which is a lot cheaper, and you can train 20 people in the same space without wasting lots of ammunition. And then a sort of more strategic kind of virtual battle space, and there's soldiers, just a bit like a real game really, but you're actually trying to emulate, copy the battle conditions rather than necessarily make it an entertaining game. And then flight simulators, obviously a lot cheaper to train people in flight simulators before going to real planes. Computer games also provide a good environment for testing ideas about AI. So, for example, I collaborated on a system we were trying to build models of the models of the neural activity that was linked to consciousness. So there's this, did I cover that? Yeah, cover that. So I collaborate on a system building these models of the neural activity linked to consciousness, and also the Google DeepMind have been, these are just a couple of examples, there's an awful lot of work on this. There's a journal called the Transactions on Computational Intelligence and AI in Games, and they've got tons of stuff on all kind of things. So my work on this area anyway, we built this model of what's going on in your brain when you're conscious, called this neuronal model of the global workspace. This was used to control this avatar in Unreal Tournament, and the idea was we were trying to produce human-like behavior, because there's this competition for human-like behavior. So we built this sort of overview of the architecture, this global workspace model, and this controlled the avatar, and there's this competition where people make a judgment about whether this avatar is behaving in a human-like way or a non-human-like way. It's a bit like a Turing test you might have heard of. So we used this architecture to control this avatar and competed in this competition, and we did all right. We came second. We probably could have done a little bit better. Google, more recently been in the news for Go, but here's an example of, which is board game, right? Sort of a board game. This is an example of using Atari games to develop artificial intelligence. So it's very nice. Atari games, you've got these simple Atari games like Pong, Boxing, Robo-Tank, Breakout. So there's a limited amount of data available in them, but you also have you have a control. So in this case of Pong, you're kind of moving this bat thing up and down to bounce the ball across. So you've got control, and you've also got a reward signal, so you can be told, you've got the game score here, which tells you whether you're doing well. So you've got everything you need to develop a very simple AI. So they built this recurrent neural network here, which was trained to learn the mappings between input to the game, i.e. the control signal, and the reward that was received from the game. And it turned out that their system could perform above human level, like vastly above human level for lots of games. So it showed that their system could learn the input-reward mappings, input-output reward mappings for lots of different games. So it's a nice way, and you can imagine that maybe it could be scaled up to more complex games, or maybe not. Maybe it would just break when you try to scale it up. There's often these issues in AI. Okay, so there's a few little applications of games, of game engines, game technology. So some technical issues, well, I talked about lag, delay between the action and reaction in the world, difficulty synchronizing the world of thousands of players, how to do the live synchronization to drive the physics, simulation, storage, damage collection, and so on. Some people might choose to attack games for whatever reason, so you've got to, and they might also choose to hack into the databases that hold all the user data, so there's usual denial of service attacks or hackers gaining access to user accounts. Cheating. Lots of players get very attached to their game and want to do really well in it for whatever reasons. So you need anti-cheating mechanisms, cheat detections. You need to build this into the game architecture, so linked up with security. Sort of slightly more social issue here. So many people play. People, again, are very attached to, for example, World of Warcraft, and they want to do better in it without actually putting the time in. So what they do is they pay people to play the game for them and gain extra powers or currency in the case of World of Warcraft. And so they're paying money and they're getting a more enhanced avatar or better game privileges or whatever. So we got this WoW 7 gold, makes about $1 million a year selling in-game advantages for World of Warcraft players. So it's estimated that there's 400,000 Asian workers employed in gold farming. So they just sit there playing the game, probably enjoyable for the first couple of days, probably gets a bit dull after that. And then maybe Americans or whatever are paying them to play the game for them so that their wizard or whatever their avatar is has more powers. That's the idea. And trade worth maybe 700 million per year. Okay, so I'm not an expert in this at all. This is just like an overview, which ties in quite nicely with the project for next term and with the internet scale application stuff that we're covering in general. So if you want to read more about it, then these are the books in the library that look most promising. So you can have a little look through those, talking about the network side. And as I said, it's a highly technical field, and I've only scratched the surface in this talk. Okay, so I've covered some different types of online games. I've been aiming to give you the internet scale application angle on this, as well as some ideas for your mini projects. And next lecture, I'm going to talk about the essay assignment for next term.